discussion is by Chaitanya Sheth, who is currently pursuing BSc third year at the Maharaja Sayajirao Rao University of Baroda. He has attended MTTS foundational courses and MTTS 2021 follow-up course and so on. So he is going to talk about an application of discrete metric spaces in coding theory. Over to you, Chaitanya.
Yeah, thank you. Good morning, all. What my theme is that, oh, sorry. Where did it go? Okay. What my theme of presentation is, we often study real analysis in our classes, some metric spaces and analysis related to it, but we come to know its applications very less often. So I have come up with an application which deals with coding and decoding of messages. So this is my plan of session. I will start with metric space, then the metric space that we need of coding, example, etc. So let us see what is metric space. Let us see that first. So suppose X is a non-empty set, then we call a mapping D from X cross X to R, or instead of R, close open interval 0 to infinity. We call it as metric if it satisfies three properties. One is non-negativity, symmetry, and the third is triangular inequality. So in terms of mathematical expressions, non-negativity is distance between X and Y, X, Y are in X, is always greater than or equal to 0, and distance 0 means X is equal to Y. Distance between X and Y is same as distance between Y and X, that is symmetry, and triangular inequality is distance between X and Z is less than or equal to distance between X and Y plus distance between Y and Z. If you are going from X to Z directly, then that distance will be less than this distance if you go via Y. If Y is here, then the distance will be equal. This is what triangular inequality says. So if these three conditions are satisfied, then we call D as metric and the pair XD as a metric space. So one of the simplest examples of metric space is this one, that suppose X is equal to R, the set of real numbers. Then for X and Y and R, we define distance between X and Y as modulus of X minus Y. It is easy to see that this D is a metric and RD is a metric space. We often refer to this as a usual metric space. So let us see what the metric space that we need, namely discrete metric. How do we define it as? Suppose X is equal to R, the set of real numbers. Then for X, Y, and R, we define D as distance between X and Y is equal to 0 if X is equal to Y. And distance will be considered as 1 if X is different from Y. So in this case, we have only two possibilities for distance, either 0 or 1. So, and both are two separate numbers, discrete numbers. That's why we call this mapping as discrete mapping. So our claim is that D is metric and RD is a metric space, and we denote this by R suffix D, where this D stands for discrete. So let us prove it. Proof is really very simple. Let us have a look. So by definition itself, the non-negativity property is satisfied that for every X and Y in R, distance between X and Y is 0, and distance between X greater than or equal to 0, and distance between X and Y is 0, then by definition, we can conclude that X is equal to Y. And similarly, the opposite implication. So this is non-negativity. Then if X is equal to Y, then Y is equal to X. So distance between X and Y will be 0. Same will be the case for distance between Y and X. If X different from Y, then Y is different from X. So both distances will be 1. So symmetry is also satisfied. For triangular inequality, we consider three cases. First is suppose all A, B, C, X, Y, Z are equal. Then all the distances will be 0. So, and we can say that 0 is less than or equal to 0. So distance between X and Z is less than or equal to dxy plus dyz. In first case, we are done. Suppose one of these is different. Without loss of generality, we assume that X is different from Y and Y is equal to Z. The case that X is equal to Y different from Z is analogous to this one. So since X is different from Y, this distance will be 1. Y equal to Z, so this distance is 0. And Y equal to Z, hence we conclude that X is different from Z. So distance between X and Z is 1. And 1 is less than or equal to 1. So in this case also, we are done. Suppose all the three are different. Then all distances are 1. And 1 is less than or equal to 2. In fact, it is strictly less than. So less than or equal to, this distance is less than or equal to this sum. Hence, we conclude that this RD is a metric space. We call it as discrete metric space. Now, how do we use it in coding? Before that, let us see what is the need of coding. So, the need is that coded messages are easier and quicker to transmit. In communication, they increase our efficiency. Also, the coded messages can be safer because the one who does not know how to decode cannot interfere in the transmission of message, and he or she cannot read what is being transmitted. And third case is, practically it is not always possible to transmit messages directly. Say for example, when the telephones and mobile phones were not there, there was a system called telegram. In this telegram system, there was one office, say at place A, and another office used to be at place B. So from A to B, they sent some message. That message used to be in coded form. It was not sent directly. In order to transmit the message quickly, they used several codings. You might have heard of this or seen this. Okay. So let us see now motivation behind the coding, error decoding, etc. See that Alice and Bob are two armed persons, army officers. Alice is sitting at the headquarters and Bob is in the warfield. And Bob wants to reach to the headquarters. Alice and Bob both have the same identical map, but only Alice knows the safe route to reach to the headquarters without entering these enemy territories. The region marked with black is the enemy territory. So Alice prepares a map. Considering this direction is north, Alice prepares a map, and this is the map. So now instead of transmitting this directly, what he does is he encodes north as 00, west as 01, south as 11, and east as 10. So the code becomes this. Now, suppose there is some error during the transmission of this code. So what will happen? Instead of this N and W, suppose by mistake this 1 has got some error and is transmitted as 00, then the Bob will go 1 unit north, and now instead of turning towards this direction, Bob will go ahead and he will straightly end up in the enemy territory. Same is the case over here. If the transmission is not properly done, that he should go south, again he will end up in the enemy territory. This is something that we don't want, right? So what we do is we add some extra digits in codes such that the error can be detected and if possible corrected. So what the digits that we add are called redundant digits because they are extra digits. So for that, these are the examples, but we will come back to this later. Before that, we need to see some definitions, etc. for this code. So first thing is Hamming metric. For measuring distances between two code words, we need Hamming metric, and Hamming metric is nothing but Cartesian product of discrete matrix spaces. Here is the place where we use discrete matrix spaces. So how the Hamming metric is defined? Suppose our code word consists of n digits. Then we take the Cartesian product of x n times, x cross x up to n times. And then for two elements, say x and y, in this Cartesian product, dn, distance between x and y, is defined as summation distance between xi and yi, I from 1 to n, where each xi yi belongs to this x. And this d is nothing but discrete metric. So distance for each xi yi, distance will be either 0 or 1. Using this Hamming metric, we will measure distances between the different codes. Okay. So what is the code? So the code means a set of different code words. For example, that set in which we encoded north, south, west, and east. North, west, south, and east. This set is called a code, and each elements are called code words. And weight of a code. For any code C, we define weight of C as minimum distance of O means 0 code, that is 0, 0, 0 n times, and x, where x is element of this C and x is different from O. So minimum distance of a non-zero code from 0 code is what we call weight. So in this C1, minimum number of non-zero digits is 1. See over here and here. So for this C1, weight will be how much? Weight will be 1. Okay. Now let us go back to that example in which this is north, west, south, and east. So instead of encoding n as 0, 0, we encode it as 0, 0, 0, 0, 1 like this, 1, 1 as this, and 1, 0 as this. So in this code C, there are at least 2 non-zero digits in all the non-zero code words. So we can say that weight of this code, weight of C, is equal to 2. Now, in this case, suppose we want to transmit the message N and S. Then the original code word will be 0, 0, 0, 0, 0, 0, 1, 0, 1. This is what we will transmit. Now, if by chance, after during transmission, some error is occurred and receiver gets scored something like this: 1, 0, 0, 0, 1, 0, 1, 0, 1. So, while decoding, the receiver will not have this. Receiver will be having this and the set, code set, this one. So what he will do, he will measure distance of received codes with each of these code words. For example, distance between this code word 0, 0, 0 and 1, 0, 0, that is 1. Distance between 0, 1, 1 and 1, 0, 0 is 3. Distance between 1, 0, 1 and 1, 0, 0 is 1. And distance between 1, 1, 0 and 1, 0, 0 is also 1. So from that, the receiver will conclude that there is some error in this code. He may not be able to correct this code, but he will at least detect that there are some errors. So when can we say that code will correct error or detect error? So for that, we have formula that if a code has weight 2t plus 1, then the code can correct at most t errors, or code can detect at most 2t errors, but not both at a time. That we should keep in our mind. Either a code can be error correcting code or it can be an error detecting code. Yeah, remember that everywhere we are measuring distances using this Hamming metric formula. Okay, so this weight of this code is 2, and we can write 2 as 2 times half plus 1. So our t is half, so not an integer. So this code will be, we will be able to just detect errors, but will not be able to correct it. We can correct from this code, we can correct at most one error. So from that, we will detect that there is some error in this, there is some error in this, and this is perfectly transmitted. It is same as this. Now, if we want the more accuracy in our course so that we can even correct the errors and correctly understand what the original code was supposed to say, then we add more redundant digits, more extra digits. Say, for example, this one. Now, instead of mapping 0, 0 to 0, 0, 0, we map it to 5 times 0. This is mapped to 0, 1, 1, 0, 1. This maps here and this is used as here. So this is north, this was west, this is south, and this is east. So now observe that there are 3 non-zero digits in each of these codes, at least 3 non-zero digits. So the weight of this code will be how much? It will be 3. And by using this 2t plus 1 thing, we can write this as 2 times 1 plus 1. So this code C can correct a single error, or it can detect at most 2 errors. So let us see how it will correct the errors. Again, we use that same message NNS. So now our transmitted message will be 5 times 0, again 5 times 0, then 1 0 1 1 0. This will be our transmission message before transmission. After transmission, suppose the message gets like this: 0 1 0 0 0 1 0 0 0 0 1 0 1 1 0. So 1, 2, and 3. Now measure distances of each of these code words with these code words given in C. So distance of the 0 1 0 0 0 with first one is how much? It just differs in one place. So the distance is 1. Then for this one, distance will be 2 because it differs in these 2 places. With this code, the distance will be 1, 2, 3, and 4 because it differs by 4 places. And distance with this code will be 1, 2, 3. 3. So now observe that this code word has minimum distance with 0, 0, 0, 0, 0. So we conclude that this message was supposed to be 5 times 0. And 5 times 0 means what? North. So this is correctly concluded. Again, in this one, in the similar manner, we can conclude that this is north. And in this one, we see that this code is same as this one. So we can directly conclude that it is S. So N and S. So we have corrected a single error in this code, and the message that was intended is the same as interpreted. Now, it is not necessary that we will always get this direct conclusion. Suppose in some case, we will get the minimum distance as 2 and with 2 codes, say like this, 2, 2, 4, 3. Suppose we get something like this. Then in this case, what we do, we have 2 options. Either we can decode it arbitrarily. Suppose our some message is given and it has distance 2 with 0, 1, 1, 0, 1 as well as 1, 0, 1, 1, 0. Then there are 2 ways. One is this one, that we can just decode arbitrarily. So it is in that case, it is on us to just choose any of these codes and decode. Maybe suppose it was west, suppose it was south, like that. Or other possibility is retransmission. we ask the sender to retransmit the code so that we can have correct conclusion. When situations like this.
Sorry for the interruption. Chaitanya, you have your last 5 minutes.
Okay, thank you. So such situations, which is war-like situation or a defense situation, we will not go for arbitrary decoding. We will ask for, definitely we will ask for retransmission. So each of these code words will be able to correct one single error, or if we choose the role of C3 as error detection, then it will be able to detect two errors, either error correction or error detection, not both at a time. Okay, so this is all about this error correction and detection. If someone is interested more, then there are concepts from which this 2t plus 1 comes. All those things need to have understanding of some finite fields, vector spaces over finite fields, linear codes, finite vector spaces, etc. For that, one can refer to Joseph Gallien's book, Contemporary Abstract Algebra, chapter number 31. I have taken all these things from this. And at last, I would like to say that it is not necessary the code will always be binary. Our code may be ternary also. In ternary code, we will use 3 digits, 0, 1, and 2. But when it comes to decoding ternary codes, we cannot just directly do this thing. This is called maximum likelihood decoding. You see, this code word was very much likely to this one. So we decoded it using this, that it is nearest to this one, so it will be north. So this is called maximum likelihood decoding. So this maximum likelihood decoding fails in ternary, quaternary, etc. codes. For those things, we need some parity check matrices and parity check properties. That's also very wide area where it has very wide scope, and it is a topic of interest for maths as well as computer application students. So if you are interested in these things, you can have a look at this book, this Joseph Gallien's book. Other things can be found in this coding theory book, and these are my references. Yeah, thank you.
Thank you, Chaitanya. That was an interesting application of what we usually read in metric spaces. Thank you. Now we are open to questions and having discussion with Chaitanya. Participants can unmute themselves and ask questions if they have any.
Yeah, Chaitanya, I have a question.
Yes, sir.
Yeah, so when you add redundant 0 and 1s, so is there a pattern how we add them, or do we add them randomly?
No, there are several patterns. One of the common patterns is using that parity check matrix. So that creating parity check matrix needs the knowledge of those linear codes and finite field vector spaces over finite fields, etc. So it was out of the scope of this 20 minutes.
Okay. So like okay, so like if n is 0, 0, and I want to add three more zeros, like say 2 zeros and 1 1. So there is a pattern in which I can add those extra 0 and 1s.
Yeah, and one common pattern
Okay, so
is like we do in linear transformations. The identity is mapped to identity. In similar way, here the 0 code is mapped to 0 code.
okay. Okay. Thank you.
Yeah, thank you.
Chaitanya, can you go to the last slide? I have to ask something
Yeah.
that we have written. Slide number 13, I think.
Yes, this is 13. Actually, those annotations I did not save.
Oh, okay. So yeah. So my question is, so after the transmission that you have written those code that for NNS, so it has total 15 digits, right?
Yes.
My question is, how do we know that there are 3 codes of 5 digits or it is 5 codes of 3 digits?
Yeah. The receiver will be having this set beforehand with him. So he knows that these are 3 words of 5 digits.
So this C is with him beforehand.
Yes.
Okay, okay.
The system was very useful and popular in the Telegram. That was quite earlier, maybe 50-60 years ago. It was very useful. Still, there are many applications of this in computer applications. Even today, this course is taught widely in computer applications.
We can wait for 1 more minute. We can give 1 more minute for people to ask question, and then we can move.
Okay, Chaitanya, this is one more question. So, have you studied this in your BSc in a course, or this is out of interest?
Some part I had studied in BSc. After that, I continued it in my interest from that book, that Joseph Gallien's book.
Gallen's book. The coding, okay, it has a chapter on coding, right?
Yes, that contemporary.
Contemporary abstract algebra.
Yes, in that book, 10th edition has chapter number 31 on coding.
So discrete metric space means you are using only the discrete metric and
Yes.
how it is applied, and you are using discrete metrics because you're transmitting the message in terms of zeros and ones.
Yes.
Okay, thank you.
Thank you.
Okay. Unless there is any more questions, we can close.
Yeah.
Okay. Thanks, Chaitanya, for this interesting application of metric space that you shared. Do you want to make any final conclusions before you move? Do you want to say anything? Okay. That's it. Thank you. Thanks again, Chaitanya. Now we can move to the next person.